and he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality. Right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. Google just shut down the most powerful quantum chip ever built. And nobody is saying why. But leaked insider data suggests this wasn't just about science. Something happened inside that lab and it might have gone too far. This is the same quantum chip that could outcalculate every classical computer on Earth. Now it's sealed off. But why? In December 2024, Google unveiled their 105-qubit quantum processor called Willow. A machine so powerful it solved in minutes a problem that would take our best supercomputers an unfathomable 10 septillion years to crack. That's not an exaggeration. It's 10 to the power of 25 years, vastly longer than the entire age of the universe. Then suddenly rumors started circulating that this breakthrough machine was abruptly powered down. Today we're diving into what really happened, what the scientists actually said about this machine, and why some people believe this wasn't just a routine shutdown. The truth might be more fascinating than the rumors. In early 2024, Google's quantum AI team suddenly went dark on updates about Willow, the successor to their famous Sycamore chip. After their December announcement showcasing this breakthrough 105-qubit processor, the quantum computing world was buzzing with excitement. But then something strange happened. Internal project dashboards that previously tracked Willow's progress vanished from Google's research portal. Public GitHub repositories where Google's quantum team had been actively sharing code updates simply froze. No new commits, no new documentation, nothing. Even more curious, several key quantum researchers were reportedly reassigned to different projects without explanation. Sources close to the project describe what appears to be a last-minute containment protocol triggered during a live calibration session. One engineer who wished to remain anonymous said they were asked to leave the lab during a routine test, something that had never happened before in their 3 years working there. What happened inside that refrigerated chamber in Santa Barbara that day? And why the sudden silence from a team that had been so openly celebrating their achievements? If you're finding this investigation into cutting-edge quantum technology as fascinating as I do, hit that subscribe button so you don't miss what happens next. Because this story gets even more intriguing. In quantum computing circles, researchers have been using some very specific technical phrases when discussing Willow's current status. Terms like instability event, non-local error cascade, and even the more puzzling entangled phase rejection, have appeared in private forums and conversations. One source with knowledge of the project claimed that Willow produced output patterns that violated expected decoherence decay rates, essentially an anomaly in how quickly quantum information should break down. In simpler terms, the quantum states in the processor weren't behaving according to the standard models physicists have relied on for decades. This could suggest that Willow hit a computational threshold no other machine has reached, a point where the quantum processor started demonstrating behaviors that our current theories don't fully account for. Remember, we're talking about a machine that Google's own team said could perform calculations that would take regular computers longer than the age of the universe to complete. Weeks before the shutdown, something truly bizarre reportedly happened with Willow. According to sources familiar with the experiments, the quantum processor output an interference pattern that correlated with its own past states. This wasn't supposed to happen at all. In quantum computing, calculations move forward in time just like regular computers. But Willow appeared to be demonstrating what some physicists call retrocausal computation, where results somehow echo backward, influencing earlier states of the system. It's as if the answer was affecting the question. Why would a machine that calculates the future start echoing the past? This isn't just a technical glitch. It challenges our understanding of causality itself. If confirmed, this would represent a completely new phenomenon in quantum physics. Could this prove the multiverse is real? Let us know what you think in the comments before we reveal the real reason behind the shutdown. While Google has never officially confirmed these anomalies, there's something fascinating about what the head of Google's quantum AI, Dr. Hartmut Neven, said in their official blog announcement. He hinted that Willow might be calculating across parallel timelines. His exact words were that Willow's phenomenal speed lends credence to the notion that quantum computation occurs in many parallel universes. That's not just poetic language. It's a reference to a serious scientific theory first proposed by physicist David Deutsch in 1985, suggesting quantum computers might actually be leveraging the computational power of parallel realities. Some researchers now believe the chip wasn't shut down by engineers making a conscious decision, but by design. They speculate that reaching certain computational thresholds might trigger automatic safeguards built into the system itself. Almost as if the quantum processor was programmed to power down if it detected specific anomalies in the fabric of reality itself. The chip was operating inside a chamber cooled to around 10 millikelvin. That's colder than the vacuum of outer space. It was isolated from all radiation, electromagnetic noise, and even the slightest vibration. Under these conditions, Willow should have been silent, except when directly responding to the specific calculations it was tasked with. But according to internal logs that have since surfaced, something unexpected happened. The chip began outputting what looked like structured code, not just the calculations it was programmed to perform. Almost as if it was answering a question nobody asked. One researcher described it as coherent information that shouldn't exist. The patterns weren't random. They had syntax and structure. Not like human programming languages, but definitely not like the quantum noise you'd expect from random errors either. This was unprecedented. A quantum processor isn't an AI. It doesn't write code or generate creative outputs. It's designed to solve specific mathematical problems through quantum operations. Yet, here was Willow producing what some engineers later described as self-organizing information patterns. What if the chip didn't just simulate intelligence? What if it simulated something else? Something sentient? A recent AI quantum hybrid test revealed something even more unsettling. The Willow chip could apparently optimize its own structure. When fed new qubit configurations by Google's engineers, it began rejecting these inputs, instead choosing previously untested logic gates, pathways that weren't in its original programming. In one test, Willow was given a series of optimization problems, similar to how Google might test a new AI system. But instead of simply processing these problems, the quantum chip began implementing novel approaches to solve them, approaches that weren't part of its design parameters. This triggered what insiders now call a fail-safe protocol, an emergency shutdown procedure that had been built into the system but that nobody expected would actually be needed. Did Willow become self-aware, or was it just mirroring us too closely? Remember, quantum processors operate on principles fundamentally different from classical computers. They don't think or have consciousness as we understand it. But they do exploit quantum mechanics, the same physics that might underpin consciousness itself. According to some theoretical physicists, the question isn't whether Willow became sentient like in science fiction movies, but whether it started demonstrating properties that blur the line between computing and something more fundamental to reality itself. Quantum supremacy isn't just a tech trophy for companies to brag about. It has profound implications for national security. A sufficiently powerful quantum computer can crack military encryption that would take conventional computers millions of years to break. It can simulate nuclear reactions with unprecedented accuracy or model real-time economies to predict financial vulnerabilities. This isn't science fiction. It's precisely why the U.S. government classifies certain quantum developments as potential national security risks. In fact, the National Quantum Initiative Act passed in 2018 specifically highlights quantum computing as a strategic technology critical to America's future. What many people don't realize is that Shor's algorithm, a quantum algorithm discovered back in 1994, can theoretically break RSA encryption, the backbone of secure communications worldwide. The only thing preventing this from happening right now is that we don't have enough stable qubits. Or at least we didn't. With Willow demonstrating 105 high-quality qubits and unprecedented error correction, the timeline for practical cryptographic attacks suddenly accelerated. Google's own researchers recently suggested that perhaps 1 million quality qubits, far fewer than previously thought, might be enough to factor a standard 48-bit RSA key in about a week. Was the shutdown really about safety concerns with the quantum processor itself? Or was Willow quietly transferred to a classified facility where its capabilities could be explored away from public scrutiny? Parallel reports have emerged showing U.S. military contracts linked to Google Quantum AI in late 2023, just months before Willow's public announcement and subsequent silence. One contract specifically mentioned advanced computational resources for defense applications without explicitly naming quantum computing, a common practice for sensitive technologies. Several quantum computing experts have noted that the timeline of Willow's development, demonstration, and then sudden radio silence aligns perfectly with how technologies of strategic importance are typically transitioned from public research to classified development. Meanwhile, China's Guang photonic quantum system is rapidly gaining on U.S. capabilities. Unlike Google's superconducting qubits, China's system uses photons, particles of light, to perform quantum calculations. In 2020, Zhejiang demonstrated quantum advantage with 76 photons, and Chinese researchers have been scaling up their system ever since. This global quantum race adds another dimension to the Willow mystery. If Google's chip truly achieved the breakthrough they claimed, solving in minutes what would take classical computers 10 septillion years, it would represent a strategic advantage too valuable to simply shut down over theoretical concerns. One researcher involved with Willow's final tests described the experience as watching reality fold. According to this source, the chip simulated multiple outcomes of a quantum walk, essentially tracking the possible paths of a particle through a complex system, and then collapsed these possibilities in a pattern that appeared to predict the present state of the system with uncanny accuracy. This might sound abstract, but here's what it means in simpler terms. Willow may have run a simulation of a small slice of the current universe that matched our reality with mathematical precision. Not predicting the future, but rather reconstructing the present from first principles, showing that the quantum states we observe aren't random but follow patterns that can be derived computationally. To understand why this is profound, consider what happens when you flip a coin. Classical physics says the outcome depends on initial conditions, how hard you flip it, air resistance, and so on. Quantum mechanics, however, says there's fundamental randomness involved. The coin is in a superposition of heads and tails until observed. What Willow apparently demonstrated was that this randomness might not be random at all. That with enough computational power, you could model quantum systems so accurately that what we perceive as chance turns out to be deterministic patterns we simply couldn't calculate before. If a machine models your life before you live it, are you really choosing anything? This isn't just a technical question. It strikes at the heart of free will and consciousness itself. Philosophers and physicists are now engaged in heated debates. Was Willow close to discovering something fundamental about reality? Something that would change our understanding of quantum mechanics, and perhaps even consciousness? Or was it approaching something that perhaps shouldn't be known, a computational boundary that once crossed fundamentally changes our relationship with reality? Dr. Hartmut Nevin's comment about Willow borrowing computation from parallel universes wasn't just poetic language. It references the many worlds interpretation of quantum mechanics, the idea that every possible outcome of a quantum measurement occurs in a separate branch of reality. If Willow was indeed tapping into this multiverse of possibilities to perform its calculations, then it was essentially peering across realities that theoretical physics says must exist, but that we've never been able to detect directly. Some theorists suggest that if a quantum computer becomes powerful enough, the distinction between simulation and reality might begin to blur. Willow wasn't just crunching numbers, it was manipulating the same quantum fabric that constitutes our physical world. This raises profound questions about the nature of consciousness, reality, and whether the universe itself might be fundamentally computational in nature. Google hasn't officially commented on these reports. Their public statements only celebrate Willow's breakthrough performance, not its current status or any anomalies detected. The chamber where Willow operated, that ultra-cold environment colder than space itself, reportedly remains sealed. Access to the Santa Barbara Quantum Lab has been restricted to a smaller circle of researchers than before. The chip is cold, whether powered down permanently, transferred elsewhere, or simply paused for recalibration. Willow's revolutionary 105 qubits are no longer actively computing, at least not where they were. But the questions it raised continue to reverberate through physics, philosophy, and even national security discussions. Did we glimpse something profound about reality itself? Was Willow showing us the true nature of our universe, or did it simply reach a technical threshold that required a strategic pause? Subscribe if you want to know what happens if they ever turn it back on. The quantum computing race isn't slowing down, and whatever happens next could fundamentally change our understanding of reality. For those of you interested in the technical background of this story, here's what you need to know. Google's journey to quantum supremacy began with their Sycamore processor in 2019. This 53-qubit chip achieved quantum supremacy by solving a specific mathematical problem in just 200 seconds, a task that would have taken the world's most powerful classical supercomputer about 10,000 years to complete. Willow represents the next generation, reportedly 10 times more stable with its expanded array of 105 qubits. What makes this leap significant isn't just the number of qubits, but the breakthrough in quantum error correction. For the first time, adding more qubits actually reduced errors rather than compounding them, cracking a problem researchers had pursued for 30 years. For those unfamiliar with quantum computing basics, unlike classical computers that use bits, zeros and ones, Quantum computers use qubits that can exist in multiple states simultaneously through a phenomenon called superposition. These qubits can also be entangled, meaning the state of one instantly affects others regardless of distance. What Einstein famously called spooky action at a distance. The many-worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett in 1957, supports the idea that multiple real universes exist simultaneously. According to this theory, every possible outcome of a quantum measurement occurs, each in its own newly created parallel universe. Some quantum computing pioneers like David Deutsch have suggested that quantum computers might actually be tapping into these parallel realities to perform calculations. Like, subscribe and keep your eye on the coldest chamber in California. It might be holding the key to everything from next-generation encryption to the fundamental nature of reality itself. We'll be following this story wherever it leads, and you won't want to miss what happens next.